Okay, so this video is to help out explain topic 1.6, which is polynomial functions and end behavior. This is the first time you're really going to probably be seeing limit notation, which talks about how a graph will proceed to the left as x approaches negative infinity and to the right as x approaches positive infinity. Okay, so it's kind of like we've talked about the interval notation, but now we're going to write it in limit notation. So as you can see, end behavior is the behavior at the end of a function, describes how it's going to behave as it moves infinitively, to the right and to the left. Okay, in other words, it's the end behavior is what happens to the y values as x increases or as x decreases. And we say without bound. So instead of saying as x continues left or x continues to decrease, we say as x decreases without bound, meaning there's no limit on it. Okay? So here in the middle, you'll notice we have, we have our end behavior and limit notation. These you're going to want to know. You will be asked to write these on the AP test. It will at some point say write the left end behavior statement or write the right end behavior statement. And it's your jobs to know if you have to include that x is approaching negative infinity there. Let me do that in green, or if x is approaching positive infinity. And that symbol, those symbols, the notation, all of it is always going to be the exact same. So you're always going to have the word lim over x and then an arrow pointing to either negative infinity or positive infinity, and then whatever the function name is. So if it's f of x, it's going to go there. If it's t of x, if it's m of x, and then you're going to put what it is approaching. A lot of times in our cases, it'll be either negative infinity or positive infinity, meaning that it'll keep going on forever and ever. But also, once we get later in unit 1, I think unit 2, just kidding, we'll have some we'll have like some asymptotes that will change the limit statements, the end behavior. It'll approach a number. It'll gradually be approaching the x-axis, but never quite reaching it. But that's more to come in unit 2. Okay, so if we take a look, left end behavior statement, if we look at this graph A, okay, this is how it's always written. It's always going to be limit as x approaches negative infinity of f of x. But how we actually say it is as x values decrease without bound, the y values of f of x approach, and then whatever the case is going to be. Okay, so if we take a look at the first example, I'm looking at the left end behavior statement. So that means I am paying attention on the left here. I notice that as x decreases to negative infinity or decreases without bound, my y values are going to keep increasing and increasing and increasing. So how we would say that verbally is that as x decreases without bound, y increases without bound. So instead of saying infinity or negative infinity in words, we say without bound. Now, how does that look for our limit statements? It's the exact same thing as you see above on the screen or on your notes. We start with the word lim. We put the x approaching, and in this case, because it's to the left, that means it's getting smaller. So negative infinity. And then this function, it doesn't really say what it is. Usually it'll say like this is a graph of f of x or g of x or t of x. So let's just say f of x because that's the most common one. And then we're going to put what it's going to. Well, we just said in words that it's increasing without bound. So that means symbolically that's going to be infinity. So that is exactly what we're going to put it equal to. Now if we go ahead and take a look at the right end behavior, now I'm looking over here and I notice as x increases without bound, as it keeps going to the right farther and farther and farther towards infinity, y is going to keep decreasing without bound or keep decreasing to negative infinity. So that's exactly how we would write it. As x increases without bound, y decreases without bound. And to write that one, it's almost the exact same as our left behavior limit statement, but now instead of x approaching negative infinity, it's going to the right. So it's increasing, it's approaching positive infinity. Still of the same function, and this time it's going to be approaching negative infinity. Okay, that's all it is. It's just a different way to write those interval notations that we've been practicing since day one. Okay, go ahead, pause the video, and give example B a try using the verbal and the limit notation for both of them, left and right. Go ahead. Okay, so hopefully you had enough time. Please pause the video if you didn't, and let's go over our answers. So left behavior verbally. Again, I notice that as x is decreasing without bound, y is also increasing without bound. So it's going to be the exact same thing as we saw to the left. The limit statement for that then is going to be the limit of x as it approaches negative infinity of f of x. That's going to also be going to infinity. Now for the right end behavior verbal statement, this time it's not approaching negative infinity as I'm going to the right, but instead it's approaching positive infinity for my outputs. So the limit statement or the behavior verbally would be as x increases without bound, y increases without bound as well. So the limit statement would be the exact same as up above, only instead of having this negative infinity, it's going to have a positive infinity. And that is the only difference. Okay? So once we have that down, then we're going to go ahead and try sketching these graphs. So go ahead and anything. It's unlimited opportunities. There's infinite number of graphs that you can create that follow those two end statements, okay, those two limit statements. So go ahead, again, pause the video and try to make a rough sketch of what you think that example would look like for A and for B. So this time we're having to do the opposite. We're having to read the limit statements and then create the graph. Go ahead. Okay, hopefully you were able to give that a shot. Again, like I said, there are so many different possibilities. What I like to do, just a little hint, and I wanted you to try to think about this on your own first, but I try to put little stars on my graph to see where it has to begin and end. Remember, we always read a graph from left to right. So as I'm reading this from the left, I know that I have to follow my left end statement or limit statement. So I know that as x goes to the left or decreases without bound, my outputs or my y values are also going to be decreasing without bound. So I would put a star there in the corner of my graph. I do it all the time. Then I'm going to go ahead and read my other limit statement, and this is my right end statement limit as x approaches positive infinity or as x increases without bound, f of x is going to decrease without bound. So again, I would go ahead and put a little star on my graph, and as long as your graph is going through those two stars, it's correct. Doesn't matter. So you could have had one as easy as a parabola upside down going like that. That absolutely would work. And you could have it as complicated as you want, just as long as it's starting and ending going down. Then for the second one, okay, I noticed that my left end statement, again, said negative infinity, so I would put my star there. My right limit statement said it goes to positive infinity, so I would put a star there. And as long as your graph is going through those two, you are good. Okay. Now, next, we have to talk about these end behaviors, because this is going to help us to determine what a polynomial looks like, along with all of those zeros, the bounces, the wiggles, the crosses that we've been working with all along this unit 1 so far. So for a polynomial equation, it's easiest to read the end behavior to the right side first. It depends who you ask, but a lot of people like to read the right side first. It's not common to do that in language arts or math, but some people read the right side when it comes to end behavior statements because we're more familiar with how a polynomial or a graph is supposed to end. So if you do it this way, okay, you go to infinity if the leading coefficient is positive. So one thing you have to check and look at is what that leading coefficient is. Now remember, leading coefficient is the number that is in front of the highest degree when the polynomial is written in standard form. So as long as you have your exponents written from highest to lowest, 5x squared plus x minus 2, then you're going to have that leading coefficient in the front. If it's not, you just have to do a little bit more looking to see where that leading coefficient would be, because it has to be with the highest exponent. If it is negative, then it's going to be going to negative infinity. Okay, so it kind of helps you to see where it's going to be ending at your graph. If then the left side, once you have the right side established, you're going to go ahead and look at if it's an even degree, the arrows have to go in the same direction. So if you had a leading coefficient that was positive and you knew that it was going to end going uphill, like up here in this example, if it was an even degree, then I know it's going to have to be on the left, that side too, because they're always going to start and end at the same direction, only if it's even though. If it's odd, they're going to go in opposite directions. So it's kind of like what you've discovered on the right side, it's just going to be the exact opposite. Okay? So let's take a look at example 3a. So here, I notice if I first start on the right side, okay, this is how we would do it using these directions. The leading coefficient here, the leading coefficient here is positive. So that tells me because the leading coefficient is positive, let's write a positive leading coefficient, then that means I know that I am going to, on the right, end high. So that is going to go to infinity. Because it's a positive, I have to end high. Then I'm going to go ahead and I'm going to look at the degree. And in this case, the degree is 5, which is an odd degree. So I know that they have to go different directions. So this means that the left would be going or heading to negative infinity. Okay? Another way you can think about that is how is it going to start and end has to make sense with that leading coefficient. Everything that we know linear. So positive we know is increasing. It's going uphill from left to right. Okay? If that's the case, then we have to start low, we have to end high. But if the leading coefficient is negative, the opposite is going to happen, and we're going to have to start high, end low. So that's another way that I've heard people do this as well. Okay? So go ahead, pause the video, and try B, C, D, E, and F. Give them a try. If you make a mistake, that's fine, but you've got to try on your own. Again, paying attention to leading coefficient. Oops, I wanted a highlighter there. Leading coefficient and the degree. Okay, so things I noticed. For B, I have a positive leading coefficient. So again, that tells me I'm going to end at infinity. It has to go uphill. Then I noticed I had an even degree, so that tells me they both have to start and end in the same position. For C, I notice I have a negative leading coefficient. So that means I don't start up, I actually start down, so at negative infinity, and then I have an even degree, so that would be at negative infinity as well. For D, it's a negative leading coefficient, so negative infinity. It's an odd degree, so that means they have to be opposite. For E, be careful because this is not in standard form, just like D. I forgot to mention that that was not in standard form. We had our leading coefficient of -1, and we have our degree of 5. Same thing with E. We have our leading coefficient of -1 and our degree of 5. So it is going to be the exact same as what we just had in D. Now for F, be careful, it's a little different because it's not in standard form. So all we have to do though is think about what would be our leading term. And if I got a leading term, I would have to multiply the 2x, the x, and the -x. That's going to give me the highest exponent. And if I multiplied those three together, I would have a -2x cubed. So that is what my leading coefficient is going to be. And that's what I'm going to think about. So I know then that I have a negative leading coefficient, which means it would have to go to the right, end my graph at negative infinity. And because I have an odd degree, it would have to start the opposite direction. Okay? So hopefully that helps you. Now, doing the same thing with A and B, go ahead and pause the video, but now this time, write the limit statements. So write your left end behavior limit statement and your right end. So you're doing the exact same thing that we just did here up above, but now you're writing this as the limit as x approaches negative infinity of h of x is equal to, and limit as x approaches positive infinity of h of x would equal negative infinity. Go ahead and pause and give those two a try. Okay, so when I did this, I noticed I would had a negative leading coefficient and an even degree. So I have those two limit statements. They both go to negative infinity, and they both have to be negative infinity because it's that negative leading coefficient. For B, I noticed I had a positive leading coefficient and I had an odd degree. So that means I would, on the right, go to infinity, and because it's an odd degree, I have to start the opposite direction at negative infinity. Okay. Now, just one more thing, just again to get that extra practice with your graphing calculators. Pause the video, graph A, B, and C on your graphing calculator. Do one at a time, I recommend, and then I'll pause it along the way too. But start with A, unpause it, see what I got on my graphing calculator to make sure you graphed it correctly, then write the limit statements, and then unpause it and check to see if you've gotten them correct. Okay, so the function, when you graphed it, that should be a parabola for A. Write the limit statements if you haven't already. Okay, limit statements would be both approaching a positive infinity. So as x decreases without bound, f of x increases without bound. And as x increases without bound, f of x also increases without bound. Now, try graphing on your graphing calculator B. And then unpause the video. Here's what you should have gotten. If you didn't get that, it's probably because you did not include parentheses around your numerator and denominator. You have to do that when you're entering these equations into your calculator, okay? If you didn't, try again, and then write the limit statements and check. These two are kind of what I was saying. It's not going on infinity. We actually have this horizontal asymptote that is at 2, which you've heard about, but we'll talk more about that again in Unit 2. So we actually say that the limits approach 2, both as x decreases and increases without bound. Go ahead and try C. That's the graph. Again, if you didn't get that, try again. But that one you really don't need parentheses for, but give it a shot. And this one, again, kind of has this unique situation where we have this horizontal asymptote. So we would actually say that both limit statements are approaching 0. Okay, that's it for limit statements. I hope that makes sense to you. If you have any questions, let me know. But otherwise, we will talk later. Bye.